I posted yesterday, and I gave you till Friday to do it. The lab should be okay as far as I can tell. It's all up and running. I will double check the dates. Make sure you get the pre-lab done before you get to lab tomorrow morning. And I also opened up the second extra credit survey. That one's designed to be done after the first exam, but before the second exam. But I still have one person who hasn't shown up to take her makeup. So I'm going to give up on that, and I will get the exam grades up this afternoon. The week is going to be a little crazy for me because we're interviewing candidates for a stockroom position. So I'm in and out with all of those, so I will get it done when I can. The fact that you got out early yesterday is because there was an entire separate section and a different PowerPoint that I didn't realize I was supposed to do yesterday. And so I'm going to lecture on that and whatever else I can today. If we don't finish up today, there'll just be a small section that we'll do on Thursday. But that's okay because the first part of chapter 17 flows right along with chapter 16, so it doesn't really make any difference if I do part of it for 16 and part of it for 17. And it's nice to see the computer decided to work today. Okay, so we left off yesterday being able to say acids are anything that have H plus concentrations greater than 1.0 times 10 to the minus 7, the concentration of H plus ions in pure water. And a base is going to be anything in which H plus is less than 1 times 10 to the minus 7. We could say OH minus is greater than 1 times 10 to the minus 7, but we want to be consistent, so we're going to talk about acids and bases in terms of H plus for both of them. We'll see in a little bit where we can use OH minuses. But I spent yesterday repeating 1 times 10 to the minus 7, 1 times 10 to the minus 7, and I've just done it twice this morning. And it's a number that is difficult to work with. It can be difficult to work with negative exponents and knowing which things are bigger, which things are smaller. So let's find an easier way to do this. And I'm sure pretty much all of you have at least heard of this if you haven't used it. And we're going to introduce the pH scale. H in the pH scale simply stands for the H plus concentration. But the P in front of anything stands for the negative log of something. Now, we've worked with the natural logs in previous chapters. This is the actual log base 10. Because we've got this times 10 to the minus 7 here. So we want to deal with the logs in base 10. Okay, so when H plus is equal to 1 times 10 to the minus 7, we're going to look at that part. We'll have to look at this part eventually. But let's just look at the times 10 to the minus 7. If you look at your calculator where it says log, the second function of that is 10 to the x. So the inverse of 10 to the x, in this case minus 7, is the log. So the log is minus 7. As long as there's just a 1 out front, it's just going to be a whole number. Now, I wrote 7 there, and I shouldn't have. I should have had another couple of zeros after it. So significant figures will come up here. Okay. So then the pH becomes the negative of -7 or +7. So this is what we consider to be the pH of pure water, a neutral solution, exactly 7. Now for acids, H plus is 1 times 10 to the minus 7 and above. And this is where students can get confused. What is bigger than 10 to the minus 7? Well, what is bigger than 10 to the minus 7 is -6, -5, up to 0. So people think, well, H plus is getting bigger. It means the exponent is becoming less negative. And when I take the log of that, the log shows up somewhere between -7 and 0, which means my pH is less than 7. More acidic means more H plus, but it doesn't mean more pH. Acidic things have the lower pHs, usually in a range from 0 to 7. Okay, dihydrogen monoxide is an acid with a pH level of 7. That's a higher pH level than any other acid. Oh my God, that's awful. When my daughter was in high school, one of the other kids in her class did a sociological survey on this for his science fair project. And it was like, okay, dihydrogen monoxide has a very high pH. It must be acidic. Dihydrogen monoxide is responsible for burns both in its gaseous state and in its frozen state. And it causes more deaths per year than any other acid. Please understand what a pH means and what dihydrogen monoxide is. What's dihydrogen monoxide? It's just water. But this is what happens when people do not have proper science training. When he did the survey, I don't know, 80% or something of the people said, oh yeah, that's awful, we should ban it. So that's just an awareness thing. Please be aware that some scientific training is important. Okay, so now for bases, H plus is less than 10 to the minus 7, which means it goes to 10 to the minus 8, 10 to the minus 9. And we're going to go up to 10 to the minus 14. So the value of the log becomes something between 7 and 14, and my pH becomes greater than 7. A higher pH is not more acidic. That's so basic. I don't know how many times I can stress that. Okay, now we had a 0 here. This would be equivalent to a 1 molar solution of HCl. We had 14 down here. That would be equivalent to a 1 molar solution of NaOH. We go up to 14 because we went down to 0, and that gives us a balanced amount on both sides. But you can go down to a negative value. Concentrated HCl is 12 molar. That's 1.2 times 10 to the 1, which would give me a -1 right there. And my pH becomes -1.08. Because like I said, this is 1. 1.2 times 10 to the minus 10 to the positive 1. That we take the negative of. And if it was just 10, it would be a negative 1 pH. We can have higher concentrations than 1 molar for strong bases. So for convenience, we say we'll stop at 0 on the bottom, and then to make it balanced, we'll go up to 14. But there are things that go less than 0 and go greater than 14. So this is just an idea of what is a range of pHs. Your stomach acid is about 0.1 molar HCl. That's why it burns so bad when you reflux or vomit. So it's got a pH down around 1 or 2. Most of your sodas have pHs down around 3. If you read the labels, they have something like phosphoric acid or some other acid in them. But they cover that sour stuff up with the amount of sugar they put in it. Vinegar has the exact same pH, but it doesn't have any sugar in it, so we know vinegar tastes sour. Orange juice, again, it's the sugar in it. It's very acidic, but it's the sugar in it that creates the problem. And just for a aside, the enamel in your teeth is basically basic, is alkaline, which means that every time you drink soft drinks or orange juice or things like that, it starts to react with your teeth, which is why dentists say either brush your teeth immediately after you have something or avoid all these acidic things. It's hard to avoid all these acidic things, I know. Rainwater is 6. Rainwater is 6 because it absorbs carbon dioxide. And when it absorbs carbon dioxide, it makes carbonic acid. So rainwater is 6. It says pure water is 7. Very seldom will you find pure water at 7 for exactly the same reason. It absorbs CO2 from the air. So when we need pure water in the lab upstairs, we boil it. I mentioned before when we were talking about colligative properties that when you heat something up and you see all those little bubbles before it actually starts to boil, that's releasing all the gases. So we boil it, release all the gases, then pour it into a container and seal it up. It maintains a pH almost at 7, but not exactly. Most water is not 7. It's mostly a little bit acidic because of the CO2. Your human blood runs between 7.35, 7.45, somewhere in that neighborhood. Seawater, because of the seashells, which are made of calcium carbonate, those are all basic. There are other salts in the ocean that contributed to this, but seawater is going to be basic. Baking soda, ammonia, washing soda, which is like baking soda, but it's used for laundry, and laundry bleach are all basic. So my pH scale is the negative log of the H plus concentration, or H3O plus concentration. And my acid strength is measured by percent ionization. Strong acids have a 100% ionization. That's our definition of a strong acid. It is not reversible. It has a 100% ionization. Because of that, we can say the H plus or the H3O plus concentration is exactly the same as the original acid concentration. These do not have K values because they're not reversible reactions. So we're just going to set the H plus concentration equal to the original concentration of the acid. Strong bases also have a percent ionization of 100%. So OH minus is equal to the concentration of base if it's a group 1A base, lithium, sodium, potassium hydroxide. If it's a group 2A base, calcium, strontium, or barium, then the OH minus concentration is twice that. So our only strong acids were given in the list: nitric, sulfuric, perchloric, perchlorous, perchloric, chloric, hydrochloric, hydrobromic, hydroiodic. But when we listed the strong bases, we listed the group 1A hydroxides and the lower part of the group 2A hydroxides And even though sulfuric acid is on our strong acid and it's H2SO4, it does not lose 2 hydrogens. But calcium, strontium, or barium hydroxide will lose both hydroxides. So you need to make sure that you know what base you're working with. The OH minus concentration will equal either the initial concentration of the base or twice that. Now, here's an interesting thing, significant figures. Somebody told me the other day that they didn't think significant figures were important unless you were told significant figures were important. Well, significant figures are important. You should always put them in, and they're based on what your problem is. When you're working with calculating pHs, you will always have a number to the left of the decimal point, 0 to 13 point something. But those values do not count in your significant figures because they came out of the exponent, and the exponent does not have significant figures. So for that first one, 1.0, I should have 2 significant figures. Whatever comes to the left of the decimal point is not going to matter. I want 2 significant figures in the decimal. So 1.0 times 10 to the minus 5, that one's easy. 1.0 gets dropped out. The pH is 5, and it should be 5.0. Okay, now, 5.0 is less than 7. 1 times 10 to the minus 5 is less than 1 times 10 to the minus, is greater than 1 times 10 to the minus 7. So that's an acidic solution. We should expect anything that has HCl in it to be an acidic solution. 0.1 molar HNO3, that's also going to be acidic because that's another one of our strong acids. Now I have 3 significant figures. That is 1 times 1.00 times 10 to the minus 1. So my pH becomes 1, and I had too many significant figures in the top one. I have too few there. No, that's right. So 1.100 has 3 significant figures. I don't count the one that's to the left of the decimal point, but I need 3 zeros to match my significant figures. Now those are easy when there's a 1 out front. And it will give me a whole number. But not every pH is a whole number because not every concentration is 1 times 10 to something. So I just plug it into my calculator. 8.0 times 10 to the minus 4. When I plug that into my calculator, when I have anything but 1, when I have 1 times 10 to the something, my pH is going to be exactly equal to the negative of that exponent. When I have something else in front of the times 10, what I should be getting is a pH slightly below what the exponent would give me. So I should find something 3 point something here. And I should have 2 decimal places, and I have 3.10. Okay, acidic. 0.0015, 1.5 times 10 to the minus 3. It's obviously going to be acidic. Again, it's HCl. Oops. Hang on. And it's slightly below 3 and 2.82. Okay, I calculated a log there. Is that the pH? No, because that's not an acid. So what did I calculate? What I calculated was a POH. When I have a base and it gives me a concentration of the base, the hydroxide in the base, then what I'm actually calculating is an OH minus, the log of the OH minus, or POH. How does the log of the POH relate to the pH? No, not how does the log, how does the POH relate to the pH? Well, I know 1 times 10 to the minus 14 is H3O plus times OH minus, and our rule for logarithms when we have a multiplication is to split it into separate logs and add them together. So I took the negative log of both sides. Negative log of KW will just be 14, because K is 1 times 10 to the minus 14. Now I have the negative log of H3O plus times OH minus. And now I can separate those. And I get negative log KW is minus log H3O plus minus log OH minus log of KW is the negative log of 1 times 10 to the minus 14. It is 14. You don't need to know all of these steps and how I got this. You just need to know what the final result is. So 14 equals pH plus POH. So if I go back to this guy, I had two options here. I could have gone ahead and used KW equals H plus times OH minus and solved for the H plus. But it's easier for me to find the POH and then say the pH is equal to 14 minus 3.10, which equals 10.90. KOH is a base. 3.1 indicates an acidic solution. I didn't want that. I wanted a basic solution. So I can calculate, whenever I'm given a hydroxide, I can calculate an OH, a POH, and therefore a pH from 14 minus the POH. And I'm going to do the same thing for the NaOH in part C. 6.6 times 10 to the minus 5 should give me a POH slightly less than 5, 4.18. Then the pH equals 14 minus 4.18, which is 9.82. So make sure when you're looking at those numbers that they make sense. A and C are bases. They have OHs in them. I want pHs greater than 7. And when I just did the negative log, that's not what I got. Now, in reverse, you have a log button on your calculator. In reverse, you use the second function above the log, which is 10 to the x, but make sure you put the negative sign back in front of the pH. If you don't, you're going to get something that's 1 times 10 to the positive 7. Not possible. So pH of 10, that's 1 times 10 to the minus 10. And notice I just have 1 times 10 to the minus 10. Values to the left of a decimal point do not count in my significant figures. And all I have in that is 1 significant figure. I don't even have 2 because there's no decimal point after the 0. So technically, there are no significant figures in that value. But I can't leave out significant figures entirely because the only things that count in a pH as significant figures are the decimal places. There are no decimal places there. So technically, there are no significant figures in that one. But the next one does. It's 1.0. That would be 10 to the minus 1. And 10 to the minus 1 is 0.1. But now, no. Sorry. I didn't want to do that. But now I have one decimal place, that's 0, so I need one significant figure. So this is either 1 times 10 to the minus 1 or 0.1. Now, pH of 10 is greater than 7, so A is basic. B, with a pH that low, is acidic. C, pH of 6, that's 1 times 10 to the minus 6. Notice now I had two significant figures in the pH, 2 zeros after the decimal place. So I have two significant figures in my answer, 1.0 times 10 to the minus 6, and this is acidic. Now, I don't have to have whole numbers like that. Whenever I have whole numbers, it's just 1 times 10 to something. I can have numbers like 12.3. Then this is 1 times 10 to the negative 12.3, and 10 to the negative 12.3 is 13. Okay, now, again, one value after the decimal point, one significant figure here. When we're going from concentration down to pH, I expect my pH to be slightly lower than the exponent that I have. So that means if I'm going from pH to concentration, my exponent should be just slightly larger than what my pH is. So 12 for a pH, I'm expecting an exponent of negative 13. 7.05, okay, this one is definitely basic. The next one is barely basic, but it is basic. So this is 10 to the negative 7.05. So I expect something with a negative 8 for an exponent. It is 8.9 times 10 to the minus 8. Now, the larger the number in front of the times 10 to is, the closer I am to that lower value. So 7.95 would be very close to that 10 to the minus 8. It might be 9 times 10 to the minus 8 or something. No, 1 times 10 to the minus 8. Okay. It's close to 10 to the minus 8, so it would be close to 1 times 10 to the minus 8. When I have something like 0.05, I'm going to be closer to the next guy, so I'm closer to the negative 7, which is why I have an 8.9 there. So if I have a value for the pH that is just under whatever my negative exponent is, then I'm going to go the other direction and say that when I'm given a pH, my exponent should be just a little bit larger than that. And where it stands is how large that value is. If I have 7.05, that's pretty darn close to 10 to the minus 7. So if I'm going to do a 10 to the minus 8, it's going to be a pretty large number in front of that 10 to the minus 8. On the other hand, if I had 7.95, that would be close to 10 to the minus 7. So that value would be a lot less. So if I did 7.95, oops. I get 1.1 times 10 to the minus 8. So all of these numbers, when we do them, are related to what that number is in the front of the decimal place. It is always 1 less than the positive value of my exponent. But how close it is to that positive value depends on how close the pH is to that number or how close it is to the next number. So again, That's basic, but barely. Now I have 10 to the minus 1.4, which gives me 4 times 10 to the minus 2. There is only one number after the decimal place, so that is one significant figure, and that is acidic. You need to be able to do both ways. You need to be able to go from a concentration to a pH. You need to be able to go from a pH to a concentration, and you have to be aware of what the material is you're working with. Is it a base that has an OH in it? If it is, then calculate a POH, not a pH. Okay, peanut butter, 6.3. Oops. The H plus concentration is just equal to 10 to the minus 6.3, which means I need to go a little bit bigger. It's -7, and it's 5, only one significant figure because 6.3 only has one digit after the decimal point. Okay. So as I said, if you have a base, the easiest thing to do is to calculate the POH and then know that pH plus POH equals 14. Now, if you look at this picture, there's absolutely no reason why we couldn't have done a POH scale. The bottom one is a pH scale. It goes from 0 for acids to 14 for bases. I certainly could have done a POH scale. Then 0 is 1 molar base, and 14 is 1 molar acid. Historically, we've just chosen to use H, not OH. Now, in general, I will point out that I've got the red end of this as acidic, the blue end is basic. That is because of litmus paper. Litmus paper is red in acid, blue in base. And we'll talk a little bit about what litmus paper is later in the class. Okay, so pH of a solution that's 6.9 times 10 to the minus 2 molar. It's NaOH. So I am going to calculate a POH first. So my POH is the negative log of 6.9 times 10 to the minus 2, which should give me 1 point something. Only one digit after the decimal place. No, actually, that's not true. I had it right the first time. I was working backwards again. Okay, I have 2 decimal places because there's 2 values in my concentration. My concentration has 2 significant figures, so my POH should have 2 places after the decimal point. Then my pH is simply 14 minus that, or 12.84. Now that 14 is an exact number. As long as we're working at 25 degrees Celsius, that is an exact number. I can put in as many zeros after the decimal place as I need for this subtraction. So the pH of this is 6.9 times 10 to the minus 2. Now, as I said, I could have done 1 times 10 to the minus 14 equals H plus times OH minus. H plus is equal to 1 times 10 to the minus 14 divided by 6.9 times 10 to the minus 2. I could have done it that way. But I've told you guys before I'm lazy. I don't want to have to deal with exponents if I don't have to. So I just find POH first. And when I find POH first, then I can go ahead and just subtract from 14. Hydroxide concentration. Hydroxide is OH minus. 7.7 times 10 to the minus 10. So the negative log of 7.7 times 10 to the minus 10 is 9.11. Two significant figures, so 2 decimal places. And then my pH is 14 minus 9.11 or 4.89. With a very low concentration of NaOH, or whatever hydroxide I have, this is going to be an acidic solution. So I wanted a lower pH. Okay, hydronium ion concentration. Hydronium ion concentration is H3O plus, or H plus, and the pH in each. So first one's easy. H plus is 0.1 molar. HCl and NaOH are both strong, which means for HCl, 100% dissociation, the H plus concentration equals the original acid. So 0.1 molar. That's 1 times 10 to the minus 1, so my pH is 1. And I only have 1 decimal place in the molarity, so 1.0. Now, B is a strong base, so its OH minus is going to be the same as its original concentration, which is going to give me a POH of 1. And then when I subtract that, my pH is 13. Okay, so I could do this because both HCl and NaOH are strong. And when they're strong, they dissociate 100%. So for a strong acid, the H plus concentration is the same as the original concentration. For a strong base, for the group 1A bases, lithium, sodium, potassium, the POH is the same as the initial concentration. The OH minus is the same as the initial concentration. But remember, if this was instead barium hydroxide, then the OH minus would be 2 times the initial concentration, or 0.2. And then my POH equals 0. Did I just lose everything? No, I was on the wrong slide. 0.7. So my pH for that is 13.3. So for the group 2A bases, you've got to multiply your original concentration by 2. It's going to raise the pH a little bit. Okay, now, finding pH, POH for a strong acid or base is fine because our concentrations just equal the original concentrations. So I can do the same thing here. For the first one, my H plus is 0.005, so my pH is 2.3. For B, my OH minus, no, for A still. They want the hydroxide ion concentration. They want OH minus. So OH minus would be 1.0 times 10 to the minus 14 divided by 0.005, or 14 minus 2.3 equals 11.7, 10 to the negative 11.7. Either way. But this time they're looking for OH concentration. For the second one, OH is easy because it's just 0.005. POH is 2.3,
and pH is 11.7. Okay, so finding pHs for strong acids and strong bases is easy. All strong acids concentrations are the same as the original concentration. For first group hydroxides, OH minus is the same as the original concentration. For group 2, it's twice that. But if we want to go into the lab and we want to do something and we want to see what the pH looks like, instead of calculating a pH, we want to measure a pH. How do we do that? Well, we can use something that changes color, depending on whether the solution's an acidic or a basic solution. These are called indicators. Indicators are weak acids or bases that change colors whether or not they have an H plus attached to them or not. So they're a certain color when they have the H plus attached in the acid solution. When the solution is neutralized and that H plus is removed, they become a different color. This set of colors, from red to green, is simply red cabbage juice. Red cabbage juice is kind of a bluish purple when it's in pure distilled water. It goes towards the pink and then the red in an acid. It goes to the blue and then the green in a base. This is one of the simplest indicators there is because it has a very distinct color change for every single pH. For most of the indicators, we don't care what the entire range is. We want to know what the color is at one specific point. So most indicators only have one color change. Now, the reaction doesn't have to be complete for us to see a change in color. Our eyes can perceive a change in color when about 10% of the initial form has been converted. And 1/10 is equivalent to 1 decimal place in a pH. Now, 1/10 is equivalent to 1 pH, which is why I can see a distinct color change with every step here, because every one of those is taking about 1/10 to get to the next color. This is the most common one we use in lab. Phenolphthalein, PHTH. We have a lot of things that start with that combination. In its acid form, it has an H on that upper left OH, and it is clear. When it becomes a base, that H comes off. That is my conjugate base of the other one, and that happens to be pink in color. Okay, it's these rings. The electrons moving in those rings are what produces the color change. And in this ring, I can attach to a lone pair on the oxygen. But on this one, I've got that negative charge as well. So that actually adds to the electrons in the ring and gives me a completely different color. Litmus paper. I mentioned earlier that we list scales. Red is considered to be acidic, base is considered to be blue. Litmus is just another indicator, but it's a convenient indicator because it comes in strips. Phenolphthalein comes in a dropper bottle, and you have to add a few drops of it. Litmus paper comes in strips. The problem is it's not very precise because it either turns red in an acid, it turns blue in a base. It can be kind of a purpley color when it's close to neutral, but it doesn't necessarily have to be neutral. So it's a very generic indicator. And there are some indicators that have an intermediate. This is bromethymol blue. And you can see that around neutral, it's green. That green is an indication that there is still some acid in there, which is yellow, and still some base in there, which is blue. And we see a distinct color change going from yellow to green to blue. Okay, if you look at this, yellow, it's got an OH to the upper right. When it turns green, it's losing that H. But when it turns blue, it's changing its oxygen's positions. And it's moving the negative oxygen to the other side. So the structure not only loses the hydrogen, but it changes where its OH position actually is. But it makes it a little easier to see these changes if we get more than one color change. And then we have these guys. They're called universal indicators. They're just a mixture of a bunch of different indicators that give you a very, very precise color change for each pH. When you're in lab, you want to do this. You will be using phenolphthalein, but you also want to use a pH meter. The pH meter monitors the electrical activity of that H+ ion. Ions conduct electricity. So it's measuring the electrical current of that H+. It gives us a much more precise value of what the pH is than any indicator can do. Okay, now for weak acids and bases. Strong acids and bases are great. Weak acids and bases, I have a reversible reaction. Because I have a reversible reaction, I'm going to have an equilibrium constant K. So I am going to find the pH by using the equilibrium to find the H+ concentration. I can't just take it from the original concentration. So I have a K value. The K value is the conjugate base, A-, times H3O+ divided by the initial concentration, HA, because water is not included because water is a liquid. For the base, again, water is not included. I have a Kb, which is BH+, my conjugate acid, times OH- divided by B. Okay, we have all sorts of Ks. I told you this the other day. We've seen a Kc, we've seen a Kp, we had a Keq, which could mean anything. We now have a Kw for water. We have a Ka for an acid, Kb for a base. Please do not confuse this Kb with the 0.152 Kb from the boiling point elevation equation. We simply do not have enough letters. I mean, with all the fighting that we did back in the 70s and 80s with Russia over naming things, I don't know why we can't stick a Cyrillic one in there, except most keyboards don't have Cyrillic things in them. And I don't even know if my Word has Cyrillic available. Okay, so some Ka and Kb values. Notice that the strongest ones are still 10 to the -4. Most Kas are pretty low. Phenol. It's that ring structure with an OH hanging off of it. Because, again, of the movement of the electrons in the ring and how they can attach themselves to the oxygen, that guy is a really crappy acid. It doesn't lose its H plus very easily. The strongest acid there is hydrofluoric, HF. It's got the largest Ka value. The biggest Ka value means the most products. On the other side, I have all the ammonia derivatives for a base. And again, my strongest ones are 10 to the minus 4. Pyridine, again, the reason it's so low is it's a ring structure. Those ring guys don't do a very good job of acting as an acid or a base. They do. When I was in grad school, we had a homework assignment in one of my classes where we had to figure out the pH of phenol. And no matter how many times I did it, I came out with the fact that it was basic. So I went to the instructor and said, will you please show me how to do this to make sure I get it as acidic instead of basic? I was supposed to be getting 6.7 and I got 7 point something. He showed it to me and then guess what? It showed up on the test and I still couldn't do it. You need to be able to find pHs of these guys no matter what their Ka values are, how strong or weak they are. Okay, so the smallest exponent for a Ka is equivalent to the lowest pH. On the other side, the smallest exponent is the highest pH because it's the strongest base. So the higher the exponent, the stronger the Ka is, and that means a stronger acid. The higher the Kb value is, the stronger the base is, and the higher the pH. So our pH scale is the negative log of H+. Our pOH scale is the negative log of OH-, which means I can basically take the negative log of anything I want. So when I'm comparing these guys, I have to figure out what the exponents look like. But let's get rid of, just like we did with the pH and pOH, let's get rid of the exponents. And let's make a new P scale. As long as P stands for the negative log, I can put it in front of anything. So let's do a pK scale. The pK scale will make it easier for me to determine which ones are the best acids, which ones are the best bases. So pKa is just the negative log of Ka. pKb would be the negative log of Kb. And we can compare these to a pH or a pOH. So I can fill all of this in and figure out which one's strong or which one's weak from the Ka values. But as soon as I put in the pKa's, I can equate those to pHs, and the lower the value, the more acidic it is. So the weakest of these acids is phosphoric with 2.16, and the strongest of them is periotic with, sorry, I'm trying to find it on the list, with a 1.14. So if I take a pKa, it's easier for me to compare them to pHs and say a low value means a strong acid. And I can do the same thing with the Kb's. Now, all of these are much closer together because they're all ammonia structures, so their pKb's are much closer together. But again, the bigger number is weaker, the lower number is stronger. So the strongest one here is the diethylamine at 3.16. That is the lowest value. And if I equate that to a pOH, a low value means a good base. Okay. Let's take a little bit of a break here because the next few things I'm going to do are ice boxes. So if you want to play a little bit, I did put in a PhET simulation, which allows you to play. You can just add some water, put a pH meter in it, and it will give you a pH. Now if I want to add some orange juice, well, I should add water first, add some orange juice, and notice my pH is acidic. It's just there to play with for a little bit, for a few minutes while we take a break. Okay, so I told you we weren't giving up on ice boxes, we're not giving up on Ks. But in general, the Ks we do in this section should be easier than the Ks that we did last chapter. So we do have to set up an icebox problem. But H2O will never be included, so I only have to do HA, H3O+, and A-. But first thing you may notice is they don't give me a concentration, they give me a pH. So I need to convert that pH of 2.2 to an H+ concentration. And then they give me 0.1 moles of an unknown acid in 1 liter, so I need to convert that to a molarity. So my H+ taken from the 2.20 is 6.3 times 10 to the minus 3. A minus has to equal H+. So my A minus is going to be the same thing. The numerator in an acid-base equilibrium is always x squared. No exception. Because the amount of H+ you make has to be the amount of A minus. Same with a base. The amount of conjugate acid I make has to equal the amount of OH minus. So numerator will always be x squared. So in this case, I know that's what I'm adding. So I'm subtracting from that. So my final concentrations are 6.3 times 10 to the minus 3, 6.3 times 10 to the minus 3, and 0.1 minus that, or 0.0937. I can now plug all of these into a K value. K is just H+ times A minus divided by HA, or 6.3 times 10 to the minus 3 squared divided by 0.0937. My Ka is 4.2 times 10 to the minus 4, which is a typical Ka value. I told you that was like some of the strongest of the weak acids we have with a 10 to the minus 4. So easiest thing about this is numerator is always x squared. If you have to get the x from the pH, that's fine, but then the numerator is still just that squared. So I got the 6.3 times 10 to the minus 3 as 10 to the minus 2.2, and then plugged it in for both H+ and A-. So pretty straightforward compared to some of the messes that we had before. I'm never going to see a 2 in front of anything here, no stoichiometric coefficients, because acids only lose one H+, and therefore I'm only going to have one A-, and I'm never going to have a 2 in front of the acid on the other side. So no 2x's, no exponents, just x squared over the HA concentration. You can do the same thing for a base. Again, water is not included. This time they give me the molarity of the caffeine, and it gives me the OH minus concentration. So that is 0.00155. That is 0, that is 0. That's going to be plus 6.18 times 10 to the minus 4. That's given to me in the problem. That's the final concentration of OH minus. It has to be the final concentration of the caffeinate anion, or cation. And then the original caffeine will be 0.00155 minus 6.18 times 10 to the minus 4, or 9.32 times 10 to the minus 4. So x squared over 9.32 times 10 to the minus 4. My KB is 4.1 times 10 to the minus 4. These are the easy ones. They gave me everything I needed to know, and I can find a K. Okay, now let's find a pH instead. At 0.1 moles of acetic acid in 1 liter of solution, so that's going to be a 0.1 molar solution. But now, I can't do this unless I have one other piece of information. That one other piece of information I need is the Ka for acetic acid. The Ka for acetic acid and the Kb for ammonia are the only ones I know. And they happen to be the exact same value, which helps me remember them. You will never be asked to guess what this Ka is. So you're either given it or the problem, or you're told to go look it up. So look it up. The Ka is 1.8 times 10 to the minus 5. So those are my initial concentrations, plus x, minus x, x, 0.1 minus x. Now, numerator is always x squared, no exception. Can we drop the minus x? Well, 0.1 divided by 1.8 times 10 to the minus 5 is 5,500, so it's greater than 1,000, so drop the x. Most of these Ka values are small enough that our final K expression will simply be x squared over the initial concentration of the acid. We'll be able to drop the x's. So my 1.8 times 10 to the minus 5 simply becomes equal to x squared over the initial concentration of 0.1. So x squared is 1.8 times 10 to the minus 6. X is equal to 1.3 times 10 to the minus 3. So x squared over the initial concentration of the acid, unless I have a very, very low concentration of an acid, this is going to work. So my final equilibrium concentrations are 1.34 times 10 to the minus 3, 1.34 times 10 to the minus 3 for H plus and OAC minus. OAC is just an abbreviation for acetic acid. So was it okay to drop the x? 1.3 times 10 to the minus 3 divided by my initial concentration times 100 is 1.34%, less than 5%. So perfectly okay to drop the x, and therefore that concentration stays 0.1. Kas, Kbs are so much easier than all the crap we did last chapter. And when we get into the end of chapter 17, they're even easier because they never have a denominator. So we gave you the worst of it in chapter 15. The Ks will get better. Okay, 0.1 mole NH3 dissolved in 1 liter of solution. Again, 0.1 divided by 1 is 0.1 molar. And Kb is 1.8 times 10 to the minus 5. Like I said, it's the only two I do not have to look up because they happen to be purely coincidentally exactly the same value, and it's stuck in my head. You would be given a chart with Kas, or you'd be given the Ka or Kb, whatever it is you need. But because of that, this chart's going to look almost exactly the same. As a matter of fact, it's going to look exactly the same, except for the fact that we're calculating an OH minus. So 1.8 times 10 to the minus 5 equals x squared. Divided by 0.1 minus x, we can drop the x. So my x ends up being exactly the same. This is exactly the same as the previous problem because the numbers are exactly the same. The initial concentration and the K values are exactly the same. It's exactly the same problem, just with a different material. Okay, so like I said, this section of Ks is going to be a lot easier than the case we did before because you can set K equal to X squared over the initial concentration unless the initial concentration is really low. As long as the initial concentration is about 0.1 or more, or even 0.05 would work, we're going to be able to drop that X. So an OH minus and a strong base, just remember it has to be multiplied by 2 for the group 2A. But H plus never has a 2 in front of it, ever. We have a strong acid of H2SO4. But that strong acid is not H2SO4 goes to 2 H pluses plus an SO4 minus. That's not the way it does it. H pluses are taken off one at a time, and each one has its own Ka value. So H2SO4, the first H comes off as a strong acid. That dissociates completely. But the second one, where HSO4 minus has to take the second H plus off, has its own Ka, and that is a weak acid, Ka. So our acids can be monoprotic, in which case they lose one hydrogen, no problem, we just do our equilibrium. Or they can be polyprotic and have 2 or 3. This is completely weak. This one, H plus plus HSO4 minus, is strong. But H plus plus SO4 minus 2 is weak. So for H2SO4, we figure out what the H plus concentration is. There's no SO4, no H2SO4 left, and I do an icebox with HSO4, H plus, and solve for SO4 minus 2. For H3PO4, I would have to do 3 iceboxes. Lose 1 hydrogen, lose 2 hydrogens, lose 3 hydrogens. So technically, I would have to do an icebox for every single one of those steps. And each one has a Ka, where this is Ka1, this is Ka2, this is Ka3. So each one has its own distinct acid dissociation constant. But once I've taken an H plus off of the acid, I now have the conjugate base, which has a negative charge to it. It becomes harder and harder to take off the next H pluses when you've got negative charges on your anion, which means that the Ka values get smaller and smaller with each removal of an H plus. So ascorbic acid goes from 8 times 10 to the minus 5 down to 1.6 times 10 to the minus 2. That phosphoric acid, 6.9 times 10 to the minus 3 for the first K. That's a pretty high K value. But then it drops to 6.2 times 10 to the minus 8 for the second step and 4.8 times 10 to the minus 13 for the third step. They get lower and lower. Going to allow us to cheat. I love these cheats. Technically, I would have to do 3 ice boxes for that phosphoric acid. But it turns out I only have to do 1. Most of the time, the first step is the only one that matters because the other values of K are so small. So I'm only going to do the first icebox. And then solve for the pH as negative log of X. Then, if it asks me, for example, if I have that ascorbic acid, and it asks me for what is the final conjugate concentration. Ascorbic acid is H2C6H6O6. That goes to HC6H6O6 minus, which goes to C6H6O6 minus. The concentration of this is just going to be equal to that Ka. Because if I do an icebox for that, the icebox will have would have and I'm just going to say HA minus goes to H plus and A minus 2. I'm going to have the same concentration of this as I have that, because the first step has to produce the same amount of H plus as it produces HA minus. So those two are going to be equal. So when I set a Ka2 equal to A minus 2 times H plus over HA minus, those two things cancel. So my second conjugate, my A minus 2, is equal to the K value, because there's H plus and the first conjugate there in equal amounts. So they cancel each other out. So hydrosulfuric acid. Hydrosulfuric acid is H2S. It's the stuff that makes rotten eggs stink. Its first Ka is 8.9 times 10 to the minus 8, but its second Ka drops all the way down to 1 times 10 to the minus 19. So without doing the icebox at all, I know that S minus 2 equals my Ka2. And then I'm going to do an icebox for losing the first hydrogen. Plus x minus x, 1.10 minus x squared times 0.1 minus x is 8.9 times 10 to the minus 8. And definitely 0.1 divided by 8.9 times 10 to the minus 8 is large enough that I can drop that x. So again, my K value is just x squared over the initial concentration. And my x value is 9.3 times 10 to the minus 5. And you can see that 9.3 times 10 to the minus 5 compared to 0.1 is negligible. It isn't very much. Oops. I cut and pasted again. So my x value is 9.4 times 10 to the minus 5. So that's my H plus and my HS minus. And when I do my check, 9.43 times 10 to the minus 5 is only 0.094% of the initial concentration. So it's perfectly okay to drop the x. So the original concentration stays the same. X squared over the initial concentration. That is the K values for an icebox, unless you've got an extremely low concentration of the material. Because even with some of these K values that we saw, even with something like this, for the most part, if I have a 1 molar solution, I'm still strong enough that I'm going to be over 1,000. So even with ones that aren't super, super low Ks, and most of them are super low, I'm going to be able to I'm going to be able to drop the x. So x squared over the initial concentration. and then just double check that your ratio of your H plus over your initial concentration times 100 is less than 5%. Now, this is not the case for base, because with bases, we're never going to have anything that picks up more than one H. So if I have ammonia NH3, it's going to go to NH4+. It's not going to go to NH5 plus 2. So I'm never going to need a second icebox for a base. And even with a strong acid, if I have more than one H, I do need more of the iceboxes, because each H comes off one at a time. So polyprotic acids, I do need to do multiple iceboxes, or I simply need to set the conjugates equal to the second and third K values. Even with a strong acid like H2SO4, H plus comes off 100% for the first step, but HSO4 minus then has its own Ka value. I don't need to worry about multiple steps for a weak base, because it's never going to pick up more than one hydrogen at a time. When it comes to the strong acids and bases, the only exception to the H plus equals the HA concentration is the group 2A bases, where you have to double the OH minus concentration. Okay. So ascorbic acid, again, without doing an icebox, the second step is going to be equal to 1 times 10 to the minus. Where the heck did I get that number from? 1.6 times 10 to the minus 12. Then I put in all my values. 8 times 10 to the minus 5. Okay, just double checking I have the correct K values, since I didn't have the correct K2 value. If I do 0.25 over 8 times 10 to the minus 5, it's greater than 1,000, so I drop the x. And again, I just have x squared over the initial concentration equals my K. X squared equals K times 0.1. X is 9.43. No. No. Again, I cut and pasted and didn't fix. H0 times 10 to the minus 5. 8.0 times 10 to the minus 6. Square root of 8 times 10 to the minus 6 is 2.8 times 10 to the minus 3. And 3 times 10 to the minus 3. So that goes in there. That goes in there. That goes in there. And 2.83 times 10 to the minus 3 divided by 0.1 times 100 is a 2.8%. So I'm okay to drop the x, and so my initial concentration stays the same. Okay, so because I didn't finish everything up yesterday, I should have introduced the pH scale yesterday, and I didn't. But because of that, I have about 10 slides left here on neutralization reactions, and then a few slides on what determines whether an acid is strong or weak. Bases are easy. It's an OH from first group or bottom of the second group, it's strong. Everything else is weak. And that just has to do with the strength of the bond. But we'll see what makes some of these strong and some of these weak tomorrow. And then tomorrow we will start, no, not tomorrow, because tomorrow's Wednesday. Thursday, we will start the first half of chapter 17, which directly plays into chapter 16. And then we should start the second half of 17 either Friday or Monday. Your test is a week from tomorrow. It is chapters 15, 16, and at least the first half of 17, depending on how far I get. Okay, your labs tomorrow. The first one is finding K values. The second one is measuring pHs. So you should have enough information now to be able to do both of those labs. Okay, have a good night, and I'll see you guys on Thursday.